so I'm Felipe Vargas, and the name of my presentation is Survival of the Fittest, Modeling the Chameleon Supernova 2014c. And that's a work done with my supervisor or in collaboration with Rafaela Margucci and her student Danielle Breteller from Northwestern University, and also with my ex-supervisor from Brazil, Giovanni Bernal. So the motivation of this work was this weird supernova Margucci had a lot of data on. So the supernova 2014c was discovered by the Lake Observatory supernova search. At first, this supernova was labeled as a type 1b supernova, and the interaction with the shock and the medium was followed in great detail for the first time. So this supernova is from a galaxy called MGC 7331 and is around 15 megaparsec from here. So that's the spectrum of the supernova about 4 days before the peak emission. So as you can see here, this is a normal type 1b supernova at early times. So if you compare with other kind of 1b supernova, it's pretty standard. And as time passed by, you can see an increment in the H-alpha line. So at first, the supernova was classified as type 1b because there was no hydrogen. And after, as time passed by, you could see an increment on the hydrogen line. The peak of hydrogen you had before the increment was from the host galaxy, and then the spectrum starts to increment the hydrogen line. So there was also a detection of the emission that fitted well with Bremsstrahlung radiation, and not as expected from a supernova that was synchrotron. So the synchrotron couldn't fit this data. And here we had an iron peak, and this is a fit made by Margucci for Bremsstrahlung radiation. So the supernova was pretty weird because, as you expected from a supernova, the emission starts to decay. But after some days after the explosion, you detect an increment in the X-ray emission. And also, so Margucci from different days of data modeled that there was an external shell on the progenitor of the supernova with this profile density. So the idea for work was to reproduce the approach made by Margucci, and so we tried to simulate that, and I made a code for Bremsstrahlung emission that calculated the interaction between the shock and outer shell modeled by Margucci. So first we had inside star simulation that was the propagation of the supernova inside the environment of the star. And after the simulation finished, here you have numerical density and radius. After the simulation finished, we take the last output of the simulation and put in a new simulation as initial condition. so we could follow the propagation of the shock in the interstellar medium. So here we have one simulation from evolving these last shock, and that's the temperature in the interstellar medium. So the shock comes and interacts with an outer shell. The problem was that even though we had around 2,000 simulations ranging the parameters for the model of Margutti, we couldn't find the profile density for the outer shell, so in a way that would fit the data. So we took a new approach that was applying an optimization algorithm to find this new profile. So we created a new code that was coupled with the hydrodynamic code and the radiation code I made. So we created an initial population of profiles, density profiles for the outer shell. Then we put mutation, and we changed this profile randomly, as it would be for the Darwin theory. For imagine that that's a genetic algorithm. So you have random mutations in the DNA for Darwin, and for us is in the density profile. So we change it randomly. Then we calculate the emission with a fitness function to compare with the data the Margutti had. So, and then we select the fittest. That's their survival. So we have a stop criteria that was the fitness function. When the fitness function is good enough, this whole process stops. So if the profile density doesn't fit the data, it goes again on this process, and you have mutations and so on. So you have many generations of simulations with random profiles. So my results are that we could find a profile density for the outer shell. Here in black, you can see the number density for this density profile, and then the interaction with the shell in different days. And here outside, so the shock wave didn't arrive, and we don't have enough data for constructing the interaction with the shell. So that's the data Margutti had for the bremsstrahlung emission. So I multiplied the lines for a number so you could see in the same plot. But here we have two main discoveries that for solar so in the model of Margutti, she applies solar metallicity, and the dotted line is solar metallicity. We discovered that for the absorption part, we should have half of solar metallicity, and then the line would be the absorption part of the bremsstrahlung emission would fit the data. Here in this region, we can see the iron peak, so we don't use the iron peak on this information because we are only comparing the bremsstrahlung emission. And we can see here that we can fit the data with this approach, with this genetic algorithm. And we discovered the metallicity of the outer shell as well. So we can see here that the profile of the outer shell follows a profile expected for an outburst, and that's a wind profile of density, and that would be an outburst profile of density. So the outer shell doesn't follow the wind behavior, and so my conclusion is, for the first time, we have applied directly this approach, this technique for a hydrodynamic simulation. We have constructed a pipeline really fast to solve difficult and degenerate problems that compares the data, so we can find profiles of density and study the median. We can apply that to more observational data, to similar events, or even to GRBs. We are working on the version of this code. So the radius behavior indicates an outburst and not a wind, as I told you before. The absorption indicates that the shell has half of solar metallicity. So as Margutti says, effectively acts as a time machine for studying stars, because when the shock wave interacts with material emitted from the progenitor before the explosion of the progenitor, we can study this material that was in the star before. So we can use it as a time machine for studying stars. So thank you. That was my presentation.
Thank you, Felipe. Question of Estefan. Estefan, do you want to ask, please?
Oh, it's a very simple question, just on which kind of, what other phenomena or object do you plan to test or to study with your code?
So the idea is that now because we needed spherical symmetry, we could apply to this transient. Now we are working in a way to optimize the code, so we don't need spherical symmetry. If I could, because the problem here is that you need a really fast simulation. So I'm working to optimize the choice of parameters, so we don't have so many simulations. It was around 100,000 simulations. So if I could do less simulations, we can apply to 2D simulations, and then we don't need the spherical symmetry. So we could apply to jets or GRBs or transients that are not spherical. So the idea is that to change the code, so I do less simulations and I can apply to Fabio's GRBs and stuff like that.
Okay, thanks.
Question from William. William, do you want to ask?
Hi, Felipe.
Hi.
So I have a question about the algorithms. In these optimization genetic things, you can sometimes get stuck in a local maximum. What do you do to avoid that? And I guess you have to be even more careful if you do simulations in more than 1D.
Yeah. So the problem is you can find minimum locals. So there are a lot of things you can do. So if you only choose the best from your genetic algorithm, you have something called elitism, which only choose the best. So if you have a minimum, your algorithm stays like stuck in this region. The idea is to choose a percentage of these best you fitted, then put some random bad mutations, and also breed them, and like you cross the genes, or you make tournament and stuff, so you have a sample that's more random.
Okay.
And with this idea, you try to escape this thing where you get stuck, this region.
Yeah. Okay. Thank you.
And last question from Diego.
Okay. So, Felipe, so where is the Bremsstrahlung emission produced? Because, I mean, it's weird. One would expect synchrotron or inverse Compton for like high energy phenomena, but Bremsstrahlung, it's sort of...
Yeah, the thing is, when the supernova, so I'm going back to the Margucci's graphic. Here is what you expect for a synchrotron emission on this frequency on this day. That's 396 days after the emission. So you have these expansions from the shock. So the synchrotron goes down with time, no?
Mm-hmm.
And then you would expect that synchrotron emission would be around here. So when the shock interacts with the outer shell, you have a break in its velocity, and that's what means Bremsstrahlung, which is like breaking radiation in German. And what you have here is that you are stopping a charged medium, and then it produces radiation because you are changing its velocity.
Okay, so it's the jet versus the medium 400 days after.
So it's the interaction between the shock wave with the medium.
Yeah.
And then when they shock with each other, you have the production of this Bremsstrahlung emission.
And this is not seen in many other supernova.
Yeah, the thing is that supernova are usually observed in the correspondent bands, so they never follow the supernova with X-ray observations for so long.
Okay.
So we have in great detail the X-ray emission for this part, and usually they it's observed in optical, and you don't expect that. So there was not a lot of information about these frequencies, so you could compare, but maybe it's very common, and we don't it wasn't followed.
Okay, thank you.
Okay.
Thank you, Felipe.
Okay.
It was a very good presentation. If anyone have more questions for Felipe, I can send you the email because Felipe loves to talk. Then we can continue with Diego, please.
Hi, good morning, everyone. I have to share the tool, or you, Rosa, you will share?
No, please, you, Felipe. You can share your screen.
Okay.
Diego is doing a big effort because it's very early in Ensenada. It's around 7.
Yes.
Not even 7 o'clock.
1 second.
Diego's an observer, so.
I am asleep.